Oh, it's an honor for me to participate in this conference. Thanks to the organizer, and pleasure to meet so many old friends here. So yesterday we tried to find out with Sasha when we met first. Yeah, so it was probably 1982, I think. Yeah, so it was probably 1982. It was, and the occasion was research on prime theta functions that they appeared for the first time at that time in the theory of integrable systems. And after that, I was following his research a lot, yeah. And with time passing, you observe that somehow all mathematical papers and all mathematical talks, with small exception, belong to two groups, yeah. First group is you don't understand really what is going on, yeah? So in this talk or in this paper, yeah? And the second group is you think you can do it better. Yeah, and Sasha's research belongs to this exception, yeah? So it's interesting, yeah? And I never had this idea that I can do it better. Yeah? So today I present you some results on orthogonal ring patterns and their relation to discrete integrable surfaces. And I think it fits to the title of this conference. You will have geometry and integrability, and there will be slightly more geometry here than integrability. This means more pictures than equations. First of all, so where we are based on. So there is a well-developed theory of circle patterns. A lot of research, and the main motivation is these circle patterns, in particular orthogonal circle patterns, are treated as a discretization of complex analysis. And all these beautiful features of holomorphic functions, of conformal mappings, are discretized quite naturally, this approach. In particular, for example, there are deep theorems actually due to Thurston, discrete Riemann mapping theorem. And for us, what is interesting is that integrable systems, integrable equations also quite naturally appear here. Just let me give you very, very short explanation how they appear. Yeah, so you consider such a flower of 5 orthogonal circles. You see this circle in the middle intersects 4 neighboring circles orthogonally in their common touching points, and you simply take the radii of these circles, yeah, and immediately you can derive this equation. It's written in a complex form, but it's really a real equation. It is an equation for the radius of the circle in the middle in terms of the circles in terms of the radii of the boundary circles. And you can recognize that it's an integrable Hirota equation.
So it's degree 4 in R.
Yeah, it's degree 4,
Why?
but actually, you see, it's complex thing. Yeah, so you just delete all
There is only
the
one,
parts. Yeah,
only one real solution.
Yeah, only one equation. Yeah, so, but it's I think the most compact way to write it.
Why it is Hirota?
There are many equations called this way. Yeah, it's one of them. Yeah, but it's Hirota equation. Yeah,
Well, it's the 6th term relation here.
5 point. So it's
Free term. Sum of 3 products is equal to 0. No, Hirota.
well. Okay, let's talk about this later. It's Hirota equation, at least one of many. Yeah. Okay, good. But now what we are doing, what we are going to do new. So we are going to generalize this. I will say later why it's useful and why do we want to generalize. And one idea which seems to be right is to generalize circles to rings. And ring is just a pair of 2 concentric circles. Now you have this blue circle, orange circle, they are concentric. And now we introduce what does it mean that 2 rings intersect orthogonally. You see to the left a pair of 2 rings. And orthogonal intersection means that an inner ring of one, an inner circle of one ring intersects the outer circle of another ring orthogonally. Yeah? So there are two these orthogonal angles here, right? That's it. Yeah. And then you consider ring patterns with a combinatorics of a square grid. You have two circle patterns with small and large circles. And here in the middle, oh, okay, I can show. Here, you see already four neighboring rings. They share a common tangent point. It follows simply from this geometry. And along this direction, two inner circles touch, along this direction, two outer circles, right, touch. Okay. Okay, so, I'm sorry. An important thing, yeah, these rings are oriented. Usually you are thinking about picture like this, but when the outer circle becomes smaller, then the inner circle can degenerate to a point, and then you go further. Again, you obtain a circle, but differently oriented. This circle in the to the right, in red, it's a differently oriented inner circle. This is important to be able to consider this ring patterns as well.
It didn't follow. Could you repeat the last contraction?
So both these, all outer circles are positively oriented, but inner circles can be negatively oriented. This is allowed, yeah? So for example, here, they're shown in red, it's also allowed. And in this case, you will see how it appears, yeah? So look at this picture. You immediately apply Pythagorean law, and then you see that the radii, the difference of the radius squared of this ring and of this ring, they must coincide. And this is, of course, true for the whole pattern, right? So what is this? It's just the area of the ring. This means that the areas of all the rings are the same. Now, imagine an outer ring, an outer circle becomes smaller and smaller. At some point, it can be smaller than the area of this global invariant of a ring pattern. Then to compare this, to repair this, you just orient the inner circle in the negative direction, and then it's not the difference of two disks areas, but the sum. Okay. Good. Okay, now we are in the plane. So it looks like this globally. You see two different directions. Here, inner circles touch, here, outer circles touch. So it looks globally. Now let us look at the equations. So we look logarithmic radii. Rows are just logs of the radii. And then orthogonal ring patterns corresponds to solutions of this equation. Sorry, just a moment. I'm not yet used to this device here. Okay, rows, you can uniformize the radii of the rings, the radii functions, yeah? You introduce quotient sinh, introduce a common variable rho, and then you uniformize the corresponding formulas, and you just have one parameter for the ring, which we call rho. For circle patterns, it will be just a log of the radius. Here, it's a uniformization parameter. This equation can be derived geometrically. You just sum all the angles around the ring and come to this equation. It is equivalent to the equation which we have seen already. It's an integrable hierarchical equation. Yeah. And it's not so interesting from the point of view of integrable systems, and actually from the point of geometry also, because we are not that far from the theory of circle patterns. Same equation. But still, you can take then the circle pattern, apply this transformation, change rho by a constant. You see there are only differences of rows participate in the equation. And then you get a ring pattern. And then you obtain such a deformation family from a circle pattern through ring patterns to another circle patterns. Here you see examples of circle pattern z squared and log of z. So here they're related to discrete linear equations, and we already investigated. Once again, so we are in the plane, we are considering ring patterns, orthogonal ring patterns, and the theory is not that far from the theory of circle patterns. Actually, with this small modification, it's very closely related.
If you have the net of centers of these circles, suppose it's given, can you always attach with this circle pattern to it, or must be a condition?
Must be a condition. So the centers should satisfy an equation. Maybe I forgot to say it's an orthogonal circle pattern. So that all circles intersect orthogonally, and the rings are also intersect orthogonally. So you can write a corresponding equation for the centers of the circles or for the centers of the rings, but that's not trivial.
And what this equation will be? Is it also Hirota?
Don't remember.
But it's also C invariant, so
Right,
circle centers are not, so this is it.
That's right, yeah. So I will come to this point, yeah. So, okay, but you see what you can do. You can solve variational problems with Neumann boundary conditions here. More or less the same things you can do with circle patterns. So, but now we will come to something which is more interesting and new. We consider orthogonal ring patterns in a sphere and in the hyperbolic space. Same definition. This is a sphere. These are concentric circles. This is a conformal model of a hyperbolic plane, also concentric circles in the sense of hyperbolic geometry, orthogonal intersection, same thing. If you do the same thing with circles, then we see that the picture is conformal. Actually, what you can do, you can take an orthogonal circle pattern on the sphere, project it stereographically to the plane, and you obtain an orthogonal circle pattern in the plane. With the rings, it's not the case. Yeah. So because after such a projection, the circles are not concentric anymore. So this is not the Möbius theory. This is not conformal theory. And from the point of view of equations, they are essentially different from the Euclidean case. So let us look what kind of equations we obtain. They're also related to integrable systems, that what we will see, and also related to constant mean curvature surfaces, which I'm going to show. Now let us look at the spherical case. We consider concentric rings with spherical hyperbolic radii, and then apply the same Pythagoras theorem, now in spherical hyperbolic geometry. These are the corresponding theorems. And then, similarly to the Euclidean case, you can immediately derive some invariants. Q, oh, God, I will show this. In the spherical case and Q in the hyperbolic case, which are just the ratios of the corresponding cosine functions of the outer and inner circles, and of course in the hyperbolic. And the same thing, Q is the global invariant for the whole pattern. Now we would like to have just one radius instead of two, or ring, and this can be done in by uniformizing these formulas in terms of elliptic functions. Yeah, so there is an elliptic function of parametrization, and this Q here becomes the modulus of these elliptic functions. So here are the formulas. So this is the equation we would like to resolve, and this is a solution. Cosinus of R, sine of R, and sine of capital R. Sn, Cn, and Dn. So and then each ring can be parameterized by parameter beta, which gives us all this radii. So we have a set of betas that parameterize as orthogonal rings. What is the corresponding equation? You remember we go around the flower once and then sum all the angles, and this gives us an equation which was a Hirota equation in the Euclidean case. The corresponding equation looks in the following way, where G is given in terms of Jacobi functions, can be computed, and the graph of this function is like this. Yeah? You see, here in the Euclidean case, we had only the differences of the corresponding parameters involved in the equation. And here we have differences and the sum. So, okay, so, sorry, what would we like to do? We would like to solve this system. So we have, for every ring in your ring pattern, you have such an equation. And you would like to find betas that solve this system. And you're on the square grid. Not Hirota. Wait a moment. Well,
System discretizes something known.
wait a moment. I will come to this, yeah. Of course, we will look at the continuous limit, yeah. Good, but that's the equation, that's the system. And how to solve it? Variational principle, yeah. If you want, you write a Lagrangian or just a functional, and critical points of this functional are exactly the solutions of the equation we have seen. This functional is a sort of an elliptic generalization of a dilogarithm function. Yeah? So it's so in the limit, when Q goes to 1, you can recover dilogarithms and hyperbolic volumes. Yeah? So anyway, this is a action function, which you are looking for critical points of this function. And if you put all phi's, so this is the sum of all edges of your square grid. And this is the sum over all vertices. Phi's are the angles at the vertices you would like to have. Typically, this is 2 pi. Yeah, so that you minimize and get.
The relation between rho and beta.
Ah, sorry, that's the same.
Beta is
It's my mistake. Rho is beta. Yeah. So
Sorry, what's quiz?
Q is a parameter. Q is a sort of a thickness of our ring pattern. Yeah. In the Euclidean case, it corresponds to the area of a ring. Yeah. So here it's also global invariant, and also it's a modulus of these elliptic functions. So geometrically, it's this geometric invariant, and analytically, it's modulus of the corresponding elliptic function. It lies between 0 and 1. Okay, now let me show you a couple of examples, yeah, how it looks like. Yeah, we're in the sphere. So this is a ring pattern, and it corresponds to Q equal to, it's almost 1, but not. And then when we are closer to 1, you see these rings, they converge to circles, orthogonal circle pattern. So in a way, it's a deformation from hyperbolic case to elliptic case. Then what you can prove mathematically, it's the following theorem for any rigid orthogonal circle pattern. If you have a circle pattern, you have this deformation for Q sufficiently small. Yeah, so that's an application of an implicit function theory. Okay. Okay, I'm sorry. So that's a story about the sphere. But here, this functional is not a convex functional. So you cannot claim immediately that the existence results you can get out of that kind. So deformation of a circle pattern. So the situation is much more favorable in the hyperbolic case. Then the relation for every ring is this one. Q again lies between 0 and 1. And it's a modulus of the corresponding Jacobi function. And this is a uniformization of the corresponding formulas. Now,
Excuse me, for that, are you still orienting?
yes, yes.
So what will you do when you change orientation?
You see, you are on the torus. And then you have, if this gamma here lies between 0 and k, so it's a period of 4k, yeah?
That's
So-
negative.
You are on this torus of the corresponding elliptic functions, yeah? So you're on the real line. And then if you are in this interval, then you have positive small r's. This means that your rings are positively oriented. If gammas are here, then they're negatively oriented. So it's 1-to-1, yeah?
U is always positive.
U is it's a parameter of your pattern. It's between 0 and 1, yeah?
But K is function of Q,
Okay, which k?
BK.
Okay, yes.
It's a K in which you.
The
put
period,
gamma.
period of.
Period is the function of Q, of course. Q is the modulus, yeah? This is your elliptic curve, yeah? So K is the period. Okay, now almost the same formula. The difference is that you have plus here instead of minus. No surprise, yeah? So the similar variational description, same function f, also with plus instead of minus, but the big difference, this functional is convex functional. So you compute the Hessian, and you see that it can be represented in this way. It's a sum over all the edges, and these terms are simply non-negative or positive. Yeah. So you see, you are looking for critical points of a convex functional. It's a pleasure, yeah. So you just minimize, yeah, and you have uniqueness, existence, and if you consider a global problem, then of course you should respect boundary conditions. But this all can be done. The tool is really this Lagrangian description, if you want, with a convex function. So the theorem is that for any choice of the boundary radii here, or angles, these boundary angles, these are Neumann boundary conditions. Yeah, so these are geodetics in the hyperbolic plane, which you see. So you align your circles along these geodetics. You can prescribe these boundary circles as you want. There exists a unique orthogonal hyperbolic ring pattern. There exists a unique solution here. You get it just by minimizing this convex function. Now about the smooth limit. So what kind of integrable systems we are dealing with, actually? Or whether it's integrable, I haven't said that yet. Yeah, but let us look at the smooth limit. What kind of smooth limit is natural? First of all rings become small, right? And this corresponds to this case. Okay, all rings become small, and moreover, they vary a little bit, yeah? So they don't jump from one small to another small a lot, yeah? So this variation of a ring is also very small. And this means that for these variables, you have that they differ just by order of epsilon. And if you look at the corresponding just standard Laplace operator at the vertex, then it should be of order epsilon squared. This means small, smoothly varying in space rings. Then it's U, which is actually the same thing as our beta or gamma, which we had before, becomes a solution to the Sinch-Gordon equation, either with plus or with minus. We know that both are integrable. We know that they have different properties, and one of them has convex action function, another one not. So it corresponds quite well to the corresponding smooth case. So in the smooth setup, we are coming to harmonic maps to the two-sphere and to the hyperbolic space. So these two cases of orthogonal rings in the sphere and the hyperbolic space. Or this means that also that we have discrete integrable sigma models, the corresponding discrete integrable sigma models. So just let me spend maybe 5 minutes on the corresponding equations, because we are doing integral theory. It fits quite well to the existing setup. So I remind you just in 1 minute what is the notion of this integrability of consistency, which is well known. You have an equation for 4 fields on a face, and then this equation is called 3D consistence. If you can put it consistently to a cube, you start with 4 arbitrary values, then apply your equation once, get these 3 white values, and then if you pass to the last vertex, then you have generically 3 different answers if they coincide for any choice of the initial data. Then this is an integrable equation, and actually this is a story about Q4 integrable equation. All such equations satisfying this consistency were classified already a long time ago. Now with Seva and Curie. And this Q4 equation is the most general equation. It's a generic equation. So it's like Pinlevé 6, yeah? So you can derive all other Pinlevés from Pinlevé 6 by coming to appropriate limits. Here it's quite similar thing, yeah? So this is an equation in elliptic functions, which is a good sign because you know we also have equation written in terms of elliptic functions. And all other equations can be obtained from it by some limits.
Elliptic functions are parameters.
That's right. Yeah, but you see, you parameterize these guys also as elliptic functions, yeah. So and then it will be an elliptic parameterization, yeah. So it will you replace x by Sn of x, yeah. So and then it will be quite similar. So it's parameterization in elliptic functions, and geometric interpretation of this equation was a lot of sort of long-standing problem, yeah. So now I think we have it, yeah. So now this is the form of the equation we obtain from, I think, from a spherical and from hyperbolic ring patterns. Again, betas are parameters that describe us rings. Right? So we have 5 of them. We have a ring in the center and 4 neighboring rings that intersect this ring orthogonally. These are beta 1, beta 2, beta 3, and beta 4, right? So, and this is an equation. Of course, it appeared, I think, many times in the literature in different contexts. I think sort of Petanza's equations, yeah. But this is a Q4 equation. Also, this is a Q4 equation. Small difference is that this Q4 equation is an equation on for 4 fields on the square, but you can pass to equation on the star when you just take 4 neighboring squares, combine them, and then you obtain an equation for 5 fields. It's a so-called Laplace form of a Q4 equation, which can be described variationally. Yeah, so you describe variationally equations on the cross, yeah.
Can you have n factors?
Well, we are considering square grid combinatorics, yeah? So this means that every circle has 4 neighbors. You can have more.
It will still be.
It will be the same thing, yeah? You just sum the angle, yeah, around the vertex.
Can you have factors where beta I minus beta j appear?
Beta, I mean, no, this one. Only this, yeah, only this. Yeah, this is equation, this should be treated as an equation for beta, given beta 1, beta 4. Yeah, so it's a sort of elliptic equation.
K prime.
That's, yeah.
K prime is a complementary period or the imaginary period of the elliptic curve here. Okay, so some computations are involved, of course, here. Yeah, so I omitted all of them. Okay, so now this is about the status of of the theory, and I think it's quite promising because you can go further. And now we switch to geometry, and I will tell you how these geometric equations in the continuous setup appear in geometry of surfaces. So stories about Sinch-Gordon equation with plus and minus signs. Actually, the equation which appears in geometry is this one. Yeah? So in here, you have a quadratic differential, the absolute value of quadratic differential squared on the Riemann surface. It's a Sinch-Gordon equation on the Riemann surface, right? And as soon as you consider surfaces with complicated topology, with non-trivial topology, of course, you should treat it globally and have this equation on the Riemann surface. It's holomorphic quadratic differential, though, so there is also a theory for this equation developed in this surface setup. What people can construct are n-noids, they're punctured spheres with ends coming to infinity like this. Yeah, so these are so-called Delaunay ends. And these are surfaces with constant mean curvature in free space. They are soap bubbles. Yeah, so they minimize their area under some difference of pressure outside and inside the surface. So these examples you see here, they were constructed using so-called DPV method, and it's an integrable method based on Iwasawa loop group factorization. So you're using Lax pairs, all this business, and it can be implemented numerically. So what is missing here that you can't really construct such examples?
Sashi, it's not integrable, or it is.
It is.
For any Q of Z.
For any Q of Z, yeah. For any Q of Z.
In which sense it's integrable?
You can write Lax pair. You can write loop group description, and then you can construct solution by Iwasawa decomposition here. So you start with something holomorphic, yeah. So and then factorize it with Iwasawa and get something like this, yeah. But it's a big theory, yeah. So I mean, this DPV method is a non-trivial thing. Yeah, it's not widely used in the theory of integrable systems, yeah. Dorfmeister Pedit Wu. So it's well established in the surface theory.
And is it possible to do the analytical continuation, so to have not Laplacian, but to have it as an evolutionary?
Oh, yeah, of course.
You have E over there.
We deviate a little bit from the topic of my talk, yeah. So, but I mean, of course, it works for any loop groups, yeah. But it depends whether you are in a compact loop group or not, yeah. Whether you have existence and uniqueness, or this factorization works in some box, yeah. Whatever, yeah. So, but in principle, locally, it can be done. It's sort of Birkhoff decomposition, yeah. Okay, let me show you just examples, smooth examples, yeah, because I would like to come to discrete examples, yeah. Yeah. So this is a periodic example. You see, doubly periodic surface. It's also a surface with constant mean curvature. You can construct such a fundamental piece and then translate it. And the question is, the problem is how to do you construct such a fundamental piece, yeah? It's a solution of a boundary value problem where you prescribe something on the boundary and solve your equation in the interior. It reminds us the situation with circle patterns or with ring patterns, yeah? So we're about to do the same. Okay, just let me show you examples. And this is also a piece which is known as Schwarz constant mean curvature surface. It's better known as Schwarz minimal surface. It's a soap bubble, yeah, with some difference of the pressure inside and outside. And when you hold these boxes, you can put it in the square box, extend it triply periodically. And when you change the pressure here, it becomes more round or maybe more minimal. Yeah? Okay, now let us switch to discrete world. So what I'm going to do, I'm going to show you how to discretize this theory using this theory of ring patterns. First of all, maybe I will not go into all details here because there is a lot of things to explain. I will show you some pictures of what kind of surfaces appear here naturally. So these are so-called S-isothermic surfaces. There are two things here. At each vertex, you have a sphere. These spheres touch. And there is an orthogonal circle passing through 4 touching points of 4 neighboring spheres. Yeah? So you have 4 spheres and then 1 circle. So there are circles and spheres here. You see here spheres, and these blue things, they are disks. You can forget about the spheres, take them all away, and see your surface is built by touching disks. Touching means not only one point of contact, but the same tangent direction. So, and if you have, for example, 4 such touching disks, then there exists a unique sphere intersecting these 4 disks orthogonally. So the spheres can be recovered from the disks. Yeah? So this so-called 4-coin lemma. Okay, so this theory was developed already some time ago. And obviously, it's invariant with respect to Möbius transformations because we are dealing with spheres and circles and they expect some given angles. It's known that it's integrable, multidimensionally consistent. So this picture with a square, which can be extended to cubic letters of any dimension, can be done geometrically here. And all this is known. So now, since the theory is integrable, these surfaces we have here, they come with transformations. Transformations, because of this consistency, they don't really differ from the surfaces themselves. Because you remember, we had the same equations on all the faces of the cube. Now you interpret this as a surface, and this is a transformation direction. So therefore, the surfaces, they come naturally with transformations, and then we define special classes of these surfaces, of these isothermic surfaces. How to define surfaces with constant mean curvature? It's a sort of little bit trickier definition. There is the so-called dual discrete S-isothermic surface. And there is a notion of Darboux transformation. Yeah? So we are all familiar with many Darboux transformations. This is one of them, and it fits well to this consistency picture. And then the condition is that there exists a Darboux transformed surface which is dual to this in this geometric way. And this is a characteristic property in the smooth world. And in a discrete world, you say, okay, I define my surfaces using this characteristic property. And then you can introduce really the notion of mean curvature. What does it mean? What is the mean curvature at this vertex? And then you see, using so-called Steiner formula, this theory is already well developed, so already some time ago. And then you see that if you do this thing, that the mean curvature is constant. So there is a well-defined definition of constant mean curvatures that are S-isothermic. Or you can say that dual isothermic surfaces at constant distance is also a characterization. So pictures look like this. And now, oops, sorry. So this transformation can be seen as a Gauss map on your surface, as a normal map. Yeah? Now you look what kind of properties of this Gauss map you have. And you see that the Gauss map of a discrete constant mean curvature surface is a 2-sphere Kirby net. A net alternatively edge tangential to 2 concentric spheres. What do you have? You have 2 concentric spheres, and this is your normal map. Yes? At each vertex, you have a normal. Now you connect this is a map, in the continuous case, it's a map to S2 sphere. Here, these normals, they have different lengths, yeah? So it's not a map to S2, but it's a map to so-called Kirby polyhedron, or generalization of it. You get a quad surface with planar quads, and these edges touch alternatively small and large spheres. Yeah, so geometry like this. Yeah. Okay. Now, how it looks like, you have such a Gauss map or Koebe polyhedron, and it corresponds to one to our orthogonal ring pattern we have started with. Yeah, so this is the orthogonal ring pattern we are familiar with. Yeah, we have seen this already. Yeah, so it can be translated. I will not explain you more. I think it was sort of clear. Now let us look how it works in reality. Yeah, this is ring pattern. This is the corresponding surface with discrete surface with constant mean curvature surface with constant mean curvature built by touching disks. Yeah? And this is a smooth surface. You see, they are very close. Yeah? This is another example. This is a discrete surface. This is a smooth one. These surfaces were obtained with this loop group factorization. Yeah, so integrable model mechanism. Here, we compute this variationally, our ring patterns, constructed then Koebe polyhedra, and then from this Koebe polyhedra, it's also algorithmic to construct the corresponding surfaces. And it's already clear that to construct reasonable examples, you should solve a sort of boundary valued problems. And these boundary valued problems you have here, so for example, that this should be built in a square box, you can translate it to the boundary value problems for the corresponding impact. Okay. So here also smooth example, the corresponding ring pattern. You see red circles appear here, so it's important to be able to change the orientation and the corresponding discrete surface. Now, minimal surface corresponds to circle pattern. And now we deform it a little bit to the ring pattern and obtain constant mean curvature surface. You see, you put a little bit more pressure inside and the surface becomes more round. Yeah? And on the level of the ring patterns, you just change this parameter Q. Q equal to 1 corresponds to hyperbolic limit, to circle patterns. So here you just see this Q as a sort of mean curvature. Good. Orthogonal ring, orthogonal circle patterns, constant mean curvature, minimal. So what's the construction? How to construct, how this works in practice and in theory? You first, yeah. So you start with some combinatorics of your curvature lines and then apply all this mechanism for circle patterns or for how much time do I have?
So it's like more.
Look at this.
Oh, yeah, sorry, more. Don't worry.
Okay. So
Oh, you had 1 hour, sorry.
yeah. So you see, it's a slightly it's a new approach also in classical differential geometry because what kind of data you are dealing with? Yeah. So you have a continuous minimal surface with combinatorial data of curvature lines on your surface. So usually curvature lines, they bring square grid, yeah? So they are intersect orthogonal, but there are some umbilic points, yeah? And all that gives you some tessellation of a sphere, yeah? So which is non-trivial thing. And this will be exactly a combinatoric which we built in our discrete setup, which we then we construct the corresponding ring pattern or the corresponding circle pattern by using this variational principle. Koebe polyhedron from the circle pattern, then discrete minimal surface. That was already a rather old story, which we did a long time before. Now, you see, we changed just a little bit. From minimal to constant mean curvature, there is a change up there. And also we change circles to rings. And then we can describe geometry from combinatorics of curvature lines, also in constant curvature case, using this ring pattern theory. Okay. So I'm not going to show you a movie about this, yeah. So, but you can find it on my webpage. There is a short movie, even with music, about how one can generate on YouTube also how to generate minimal surfaces using Köber polyhedra. This is a circle pattern case. Yeah. So here in the ring patterns, this is new, and this is quite similar. Now let me show you how they look in 3D. Yeah, so they are these plaster models of smooth and of discrete constant mean curvature surfaces obtained by quite different methods. And the question is about convergence. So if you would like to do something reasonable in differential geometry, then it would be good to prove that there is a convergence here. This convergence is proven already in the minimal surface case. That's a circle pattern theory. It's even proven that this is a C infinity convergence, the convergence with all derivatives. So we expect that it's also true for the rings. So, but it's not yet done. What you see, you can compute these models numerically. And if you then take a smooth model, take a discrete one, these pieces are congruent in the smooth world, but you put the discrete one on the smooth one, and you see they fit absolutely perfectly. Yeah, so you can even build something architectural from this. Yeah, yeah, which is a good indication for
3D printing.
it's 3D printing. Yeah, yeah, yeah. So it's a real thing. Yeah, so it's photo. It's wait a moment.
Ah, you're giving one to Sasha.
So that's a story about C infinity convergence. So it's not yet proven. It's not yet proven, but I do believe that it can be done, and there are some indications that it's really the case. This is a numerical indication.
By 3D printing.
Well, you have all computer data, yeah, but yet 3D printing is the last step, yeah, yeah. So now you see, this is an image from our new paper with this Iwasawa loop group decomposition and DPV method for Schwarz constant mean curvature surface. And this is a corresponding picture from a quite recent paper with Hoffman and Smink on discrete constant mean curvature surfaces. Yeah, just find the difference. Yeah. So this is smooth, this is discrete. Yeah. So of course you can refine it by adding more and more circles or more and more disks. Then you pass to this continuous limit. It will be Sinch-Gordon, as we have seen analytically. So it's not surprising that we have such a good convergence. Now, something about future. Yeah. So what can be? Yeah.
You have this blue and white color on the left.
Yeah.
Can you remind?
We made it for a mathematical calendar. Yeah, so it's an artistic thing. Yeah, so these two pieces, they are congruent. You just build this piece and then reflect it this way, and build the whole surface. Yeah, so it's a factor of this thing with respect to the corresponding symmetry group. Yeah, it's a quadrilateral. Yeah, you do the same here.
Fundamental domain.
Fundamental domain. Yeah, discrete symmetry group. Okay, good. Now, what can be done? So there is a very closely related theory of minimal surfaces in S3. Actually, minimal surfaces in S3, they are isometric to constant mean curvature surfaces in R3. So this means that, in principle, they correspond to the same equation of the Sinch-Gordon equation. But now the question is how to use it, how to build your surface using this solution, right? So this is so-called Lawson correspondence, which is already known on the level of frame. So there is a notion of discrete Lawson correspondence. It's almost there, but not yet quite. Yeah. So it's as I said, it's outline, yeah? So what can be done? Here you see minimal surfaces in S3 after stereographically projected to R3. They look like this, and there is a lot of research about these surfaces. And this means that we have spherical orthogonal ring patterns described by integral Q4 equations, which we have seen, with a variation principle. And I hope that next time I will be able to show you these surfaces built out of these points of various radii. Yeah? So discretization of this. Yeah? So now it's not yet developed. What about this hyperbolic thing? Yeah, you remember it was a different version of the Sinch-Gordon equation. And if you do the same thing here, then I didn't tell about this, but you obtain constant Minkowitz surfaces in the Lorentz space, R21. Yeah, so with different signature. And constant Minkowitz surfaces in R21 are isometric to minimal surfaces in anti-de Sitter space. So this means that if all this program will be realized, then you can take this hyperbolic orthogonal ring patterns.
Center is and hyperbolic is the same thing. Or
No, not the same.
it's signature to one also.
No,
It is three. See,
it's three-dimensional space.
yeah,
It's
but
three-dimensional. It's three-dimensional space.
which signature?
Two.
Okay.
So okay, but metric is it will be positive metric. It will be Euclidean, right? On the surface.
So, yeah.
So now we are looking for minimal
It's a space.
space-like. Yeah, surfaces are space-like. Yeah, that's the theory about space-like. Yeah, space-like surfaces in R21 and space-like surfaces in anti-de Sitter. Yeah. So here this is an example. Also a trinoid sphere with three punctures. There's a minimal surface in anti-de Sitter space obtained by this Iwasawa decomposition method in the smooth. Right? So now you see, if we will be able to realize all this program in the discrete case, then what we will obtain? We have a hyperbolic orthogonal ring pattern. We constructed already constant Minkowitz surfaces in R21 using this orthogonal ring pattern hyperbolic. They are isometric to minimal surfaces in anti-de Sitter. So I hope that such a surface can be also constructed out of disks. And in this case, you obtain sort of discrete strings, right? Minimal surfaces in anti-de Sitter. Yeah. Moreover,
Space-like.
right? Space-like, but with convex variation principle. This means that you will be able to prove existence and uniqueness and all that stuff. Yeah. Similarly, as we did for these SIMC surfaces. Yeah. So that's what we plan to do next. Yeah. So now that's a list of papers. I was using these two small papers, and these are discrete papers about rings. So some of them are quite recent. That's a picture of integrable geometry, which we would like to have in this conference, and about its integral discretization. Yeah, so that was sort of theoretical research, but if you're thinking about practical applications, this kind of research is used for conformal parametrization of surfaces. So here you see an example. Yeah, so of two surfaces. This is a surface of genus 1. This is a surface of genus 2. And
One
half. Sorry?
letter is missing.
One half of the audience, I think, can guess what's the reason why I have shown these particular surfaces of genus 1 and genus 2. So because in Russian, Alexander Veselov is written this way. Yeah, so this is Russian V.
Alexander Bobenko.
Don't spoil the story. So, and this is really a practical application. And you see, this is a story about very closely related to the theory of circle patterns. Now we modified this theory. Why? What for? Practically, just to have a little bit more room. Yeah. So if you find such a parameterization, it's beautiful. I like it, but you have very huge squares here, and very tiny here, and you have no freedom at all. It's conformal mapping. Yeah. So it's rigid. But if you can come somehow to quasi-conformal mapping, so to make the space a little bit larger, then you will be able to get such a letter the same, similar, but with squares here about the same size, so not such a huge deviation of a conformal factor, right? So that's research for future if you are talking about applications. And I thought in Great Britain, especially now, it's very important to be oriented a little bit in this direction. Yeah? And I would like to present one of such surface. Yeah. A lot. Yeah. So that's a surface from this picture. Yeah. Thank you, Alexander. And
Thank you.
thank you.
You got any questions?
Can you take a good limit to goes to zero? Without
It's
trivializing?
not a good limit. Yeah.
No,
Mm.
it's
Good
never a
limit
good.
is the limit.
I said, can you take a good one? Can you make it good?
I don't know. Yeah. So I actually don't know what is this limit. Yeah, it will be some degeneration of your elliptic curve. Yeah. So, but not the one which comes in this theory. Yeah. So, but in principle, it's possible. I don't know. Yeah. So I don't expect that it will be really important, but who knows? Yeah. So you never know.
And what about the minimal surface in just ordinary hyperbolic space? There is a Koch-Gordon instead of Sinch-Gordon.
It's not there. It's not there. Yeah. So in smooth case, it's called Gordon. Yeah. So you develop a similar theory. Yeah. But should be modified. So
I don't know if
I don't know how to do it discrete. But it's quite believable that it's. I simply never thought about this. Yeah. Yeah.
Nikolai.
We have a kind of Newtonian version of this theory.
My favorite picture is Lagrangian. Yeah. So therefore, we'll look at the equations on the cross, all this. Yeah, just to compute this by variational methods. Yeah. Hamiltonian. I don't know. Yeah. So you see, we have elliptic versions of all these equations were elliptic. Yeah. Yeah. So and then it's more natural to consider its variation.
So you have this space-like surfaces in R21.
Yeah.
These are not space-like.
That's why we are considering space-like. I understand that. So from in the continuous case, okay, you can change, of course, all the signatures and the equations are about the same, but in the discrete case, it's a huge difference. Yeah.
From Q4, you can get elliptic discrete Panabé equations, right? So are there special orthogonal ring patterns described by them?
I don't know yet, yeah. So, but I can guess, yeah. So, because we have experience with circle patterns, and there is a circle pattern which discretizes z to the alpha, yeah, or z to the square and stuff like this, yeah. It is described by a Penlevé equation, yeah. So, you can play the same game, some autonomic reduction. So you have Lux representation, you can derive the corresponding, I think, Penlevé equation from Q5. And in the smooth case, it corresponds to so-called Smith surface with one umbilic point on the top and rotationally symmetric inometric. Yeah. So something like this probably can be done in a discrete case. Yeah. So first step is to do it for ring patterns. Yeah. Yeah. It's not yet done. In the sphere and in the hyperbolic space. In the plane, it's clear, yeah. So because it's more or less the same theory.
Okay, let's thank Sasha again.
Давайте.